An extraordinary and captivating phenomenon has recently unfolded in the world of astronomy, drawing the attention of researchers and enthusiasts across the globe. The interstellar comet known as 3I/Atlas has become the center of an astonishing discovery following the work of astrophotography specialist Frank Nebling, who on November 9, 2025, captured an image that reveals an extensive and radiant tail accompanied by a surprising ejection pointed directly toward the sun. This photograph exposes a structural complexity never before documented in an interstellar object, reigniting curiosity surrounding the nature of 3I/Atlas. The timing of this observation coincides with a newly published article by renowned Harvard astrophysicist Avi Loeb on the Medium platform, in which he describes the impressive large-scale structure of the comet's anti-tail and ejection streams. In his detailed analysis, Loeb examines the comet's unusual stream patterns and raises groundbreaking questions about its true nature. The central inquiry is whether humanity is witnessing a typical interstellar comet formed through natural cosmic processes or encountering something far more extraordinary, possibly even a technologically propelled vessel. While such speculation might seem bold, it is crucial to emphasize that Loeb is not engaging in unfounded theorizing. Rather, he is presenting hypotheses based on concrete and observable evidence. He explains that although 3I/Atlas most likely behaves like a natural comet, its unexpected acceleration, variations in brightness, and now the development of multiple tail structures require deeper scientific investigation. Nebling's photographic record is truly remarkable, presenting two visually striking features: a luminous, fan-shaped tail extending away from the sun, and a narrower, more concentrated stream angled in the opposite direction, toward the sun itself. This unusual configuration has left numerous astronomers perplexed, as comet tails traditionally move away from the sun due to the force of solar radiation and the momentum imparted by solar wind. Observing an ejection pointed toward the sun is exceptionally rare, and when such events do occur, they typically indicate highly localized activity on the comet's surface. The expansive tail, often referred to as an anti-tail, appears to stretch across millions of kilometers in the vacuum of space. Such a structure forms due to the relative alignment of the comet, Earth, and the sun. When Earth crosses the comet's orbital plane, the distribution of dust can create the visual illusion of a tail pointing toward the sun. Yet in the case of 3I/Atlas, ordinary geometric explanations do not fully account for what is being observed. Multiple distinct streams and flows are visible, suggesting this is not just an optical trick, but a physically real and complex structure. The fascination surrounding this object is heightened by its interstellar origin. As only the third confirmed interstellar visitor, after Oumuamua in 2017 and 2I/Borisov in 2019, 3I/Atlas enters a rare and enigmatic category. Each of its predecessors stunned scientists in unique ways. Oumuamua displayed anomalous acceleration without any detectable tail, whereas 2I/Borisov behaved like a conventional comet despite originating beyond the solar system. Atlas, however, seems to combine features from both, presenting clear cometary activity while also demonstrating unusual, unexplained dynamics. Astronomers have been monitoring the object since mid-2025, noting several behaviors that challenge established theoretical models. After its closest approach to the sun, it experienced a slight acceleration, and radio emissions detected by South Africa's Meerkat telescope revealed signals consistent with hydroxyl molecules, evidence of water vapor release as a result of heating. While these emissions aligned with expectations for a comet, the latest images now present unprecedented visual features, namely the large-scale anti-tail and the luminous ejection directed sunward. In his recent analysis, Avi Loeb explains that if the object is purely natural, the sunward ejection could be caused by uneven heating across its surface. When solar radiation reaches patches of ice on the nucleus, the material sublimates and expels gas and dust at high speeds. Depending on the comet's rotation, These jets can momentarily be directed toward the sun. However, Loeb notes that if the direction of ejection changes in a way that cannot be explained by rotation patterns or solar heating, it may hint at unknown physical phenomena. Although this does not imply artificiality, it does suggest that more rigorous investigation is needed. Loeb's Galileo project has spent years observing interstellar objects with the aim of distinguishing natural behavior from any potential technological signatures. He also points out that another recently identified object, designated C/25V1, appears unrelated to Atlas. Though located between the comet and Earth, it follows a completely different orbital path. Unless Atlas possesses propulsion, which currently lacks any supporting evidence, the two bodies must be considered independent. Even so, the coincidence of their discoveries has fueled global curiosity and scientific interest. As Atlas approaches Earth in December 2025, astronomers anticipate a rare opportunity to analyze its structure with unprecedented detail. During this period, scientists will measure the velocity, density, and chemical composition of its ejections. By comparing observational data with computer simulations, it may be possible to determine whether the comet's recent acceleration can be fully explained by natural outgassing or whether additional forces are contributing. Several major observatories, including the European Southern Observatory's Very Large Telescope and NASA's Hubble Space Telescope, are organizing observation sessions for the coming months. The James Webb Space Telescope may also capture infrared data capable of identifying organic molecules and complex hydrocarbons, providing clues about the comet's origins. Meanwhile, the Juno spacecraft, currently in orbit around Jupiter, plans to direct its radio instruments toward Atlas in March 2026, when the comet will pass approximately 53 million kilometers from Jupiter's orbit. This moment may reveal whether the previously detected radio signals persist or change as the object continues its passage through the inner solar system. A number of emerging theories attempt to make sense of Atlas's unusual properties. While the prevailing scientific consensus holds that the comet is natural, a few peculiarities continue to stir debate. The first involves the persistent clarity of the sunward ejection. Normally, such a jet would disperse rapidly due to solar wind. Yet in Nebling's image, it appears sharply defined and luminous. This could indicate unusually intense output or the presence of denser-than-expected particles. The second peculiarity concerns the symmetry and stability of the antitail. The debris appears perfectly aligned with the comet's orbital plane, implying a remarkably stable rotation for an object traveling at about 100 kilometers per second. Such stability is uncommon and intriguing. The third issue relates to the comet's slight acceleration observed in October. While originally attributed to outgassing, ongoing data collection will reveal whether this explanation suffices or whether some additional mechanism is at work. Loeb's perspective emphasizes the importance of following the evidence wherever it leads. He views 3I/Atlas as a natural laboratory for studying interstellar objects and cosmic processes. If all of its peculiarities can be explained through natural cometary physics, then scientists gain insight into how icy bodies endure and evolve over millions of years while traveling between star systems. If, however, anomalies emerge that cannot be attributed to known natural mechanisms, then researchers must remain open to more unconventional explanations. Loeb recalls that Oumuamua acceleration could not be accounted for by outgassing or radiation pressure, especially since it displayed no visible tail. That mystery remains unresolved, and Atlas now provides another opportunity to investigate the mechanics of interstellar objects with more advanced instruments. Loeb also highlights the importance of interstellar visitors as carriers of material from distant planetary systems. Examining their composition allows scientists to indirectly study planets that orbit other stars. Each such object is a preserved fragment of its home system's chemical and physical conditions, traveling across the galaxy for millions of years before entering our observational reach. At present, Atlas continues its luminous journey through the inner solar system, illuminated by the sun's radiation. Its brilliant tail stretches across space, shimmering with particles born in a distant star system. Jets erupt from its nucleus, one streaming toward deep space, the other pointing toward the sun, while the anti-tail spreads behind it like a thin veil, reflecting sunlight back toward Earth. Telescopes across the world track it nightly as astronomers document its ever-changing features. During its closest approach in December, the comet will grow brighter, becoming visible to amateur astronomers using modest equipment, appearing as a diffuse glow in the constellation Capricorn. Professional observatories will analyze its spectrum, searching for unusual isotopes that could confirm its interstellar origin. Each new observation adds a